Welcome back to Calculus 2. I'm Dr. Jeff Groh. Today, we're going to talk about improper integrals. I like to joke with my classes. What is an improper integral? An integral that does inappropriate things in social settings, of course. Not really, but to motivate the definition of improper integral, I'd like to go through an example. Let's try to integrate from -1 to 1 the function 1 over x squared dx. What do you think we'll get? Let's try, stupidly, to apply the fundamental theorem of calculus. If we just rewrite this as x to the minus 2, you might think, well, add 1 to the exponent, divide by the new exponent, and evaluate at the endpoints and subtract. This gives us -1 over x, evaluated from -1 to 1. Plugging the 1 in, we'll have -1. And we have to subtract what we get when we plug in -1. Negative will be +1. The outcome is -2. I want you to think about this. -2. Let's look at this function. This function, 1 over x squared, has a vertical asymptote at x equals 0 and goes to 0 in both directions as you go out to either -infinity or +infinity. So if we integrate from -1 to +1, how is it even possible for a function that is non-negative to produce a negative area? Oh no, this is really bad. This isn't going to work. -2 is not the answer. What is going wrong? What's wrong is that we use the fundamental theorem of calculus. If you think back about our proof of the fundamental theorem, what was the requirement for the function f, the integrand? The integrand had to be continuous, or at least piecewise continuous. This function has an essential singularity at x equals 0. It's going off to infinity. Something's definitely not right here. There is a way that we can fix this. It involves backing off from the problem areas, namely the discontinuities, and then taking limits as we go back towards them. I'll show you how this is done. In order to properly evaluate the integral as x goes from -1 to 1 for the function f of x equals 1 over x squared, we have to back off from the problem points. Let's back off. Let's say a and b. We'll calculate these areas, but then we'll take the limit as a goes to 0 from the left and as b goes to 0 from the right. So here's what we'll do. We have to evaluate each of these limits separately. Instead of integrating from 1 to 1, 1 over x squared dx, and attempting to use the fundamental theorem here, what we'll do is we'll take the limit as a goes to 0 from the left of the integral from -1 to a of 1 over x squared dx. On this limited domain, our integrand is continuous, so we may use the fundamental theorem here, and hopefully the limit will tell us whether the value of the integral is finite or not. Plus, the limit as b goes to 0 from the right, integral from b to 1, 1 over x squared dx. We're backing off from the discontinuity and then taking the limit as we go back towards it. This is a legitimate thing to do. The fundamental theorem is fully justified on each of these backed off pieces. So we get the limit as a goes to 0 from the left. We have -1 over x evaluated from -1 to a. And then the limit as b goes to 0 from the right, negative 1 over x evaluated from b to 1. That's the limit as a goes to 0 from the left. We'll have negative 1 over a minus positive 1 plus the limit as b goes to 0 from the right. Plugging in 1, we get negative 1 minus a minus 1 divided by b. Let's see what we get now. On the first term, note that as a is going to 0 from the left, a is going to be a little bit negative. Negative divided by negative is positive, but a is tiny. And everyone knows 1 over tiny is huge. This is a basic mathematical principle. So, as a goes to 0 from the left, this first limit will go to plus infinity. What about the second limit? We have minus, minus, that's a plus. This minus 1 won't matter because as b goes to 0 from the right, the second term is going to infinity. We say the whole thing diverges to plus infinity. If one of these two limits fails to exist, the improper integral is said to diverge. Otherwise, if both limits exist, then the integral converges to the sum of those limits. You can see in this last example this thing goes off to infinity, and in fact we get an infinite area. Another thing that can happen, though, is one of the limits of integration could be infinity. How do we handle this situation where the function's tending to 0? The question is, even though this trails out to forever, do we trap only a finite area, or is it going to be an infinite area? There's only one way to find out. Back off to some point L and take a limit as L goes to infinity. This will be the limit. As L goes to infinity, yes, we're going to go to L. The integral from 1 to L, 1 over x squared dx. That's the limit. As L goes to infinity, we had negative 1 over x evaluated from 1 to L. We'll write that as the limit as L goes to infinity of negative 1 over L minus negative 1 over 1. As L goes to infinity, this first term goes to 0. The whole limit is 1. This area is finite. Even though it goes off forever to infinity, it traps only an area of exactly 1. So what makes an integral improper? Basically, infinities do. But there's two ways infinities can enter. Either the function goes to infinity at some finite value of x, or the domain of the integral goes off to infinity or minus infinity. So we'll give the following definition. We say that an integral is improper if the integrand is not continuous at some point on the closed interval from a to b, or one of the limits of integration is plus or minus infinity. So if you're integrating out to infinity, you're not guaranteed to trap only a finite area. You need to back off and take a limit as you go back towards it. If you have a discontinuity, you need to back off from the discontinuities and take limits as you go back towards that. However, there are some additional rules for evaluating improper integrals. First, you have to separate the integral into several different integrals, possibly, so that you have at most one limit, one problem per integral. So if you have multiple problems, multiple discontinuities, or two limits that are going up to plus infinity and minus infinity, you have to separate this into several different integrals. First, one limit per integral, and then if one of those limits does not exist or diverges, then the whole thing diverges. So the procedure divide the integral into pieces. Each piece gives rise to one limit. If one limit diverges, the whole thing does. The whole thing does. Let's suppose we're integrating from 1 to infinity 1 over x dx. 0 is a point of discontinuity, but it's not in the interval from 1 to infinity. So the only limit we have to take is the one involving infinity. We'll take the limit as L goes to infinity, integral from 1 to L, 1 over x dx. Now the fundamental theorem of calculus is a perfectly legitimate thing to apply. We'll have the limit as L goes to infinity, natural log absolute value of x evaluated from 1 to L. The log of 1 is 0. We'll get the limit as L goes to infinity, natural log of L, and the log function as you go to infinity goes to infinity. The original function is 1 over x. We're finding the area under the curve from 1 to x. We find out it's related to the limit of this log function. The area continues to grow without bound. The whole thing diverges to plus infinity. In this case, we can determine where it diverges to. Other functions, it just diverges, and there is no sense of 2 minus infinity or 2 plus infinity. But in this case, this definitely diverges to plus infinity. We trap an infinite area underneath this curve, despite the fact that it's being pinched off as we go to infinity. The last couple examples raise some questions. What if I'm integrating from 1 to infinity, 1 over x to the power of some power p? We'll assume here that p is not 1. We already know what happens in that case. P is 1, it diverges to plus infinity. What happens in the case that p is not 1? You have to, of course, back off and take the limit as L goes to infinity, the integral from 1 to L. We'll write this as x to the minus p. That way, we can apply the fundamental theorem of calculus at this point. We'll get the limit as L goes to infinity, x to the 1 minus p over 1 minus p. We're adding 1 to the exponent and dividing by the new exponent. This gives us the limit as L goes to infinity, L to the 1 minus p over 1 minus p minus 1 over 1 minus p. What happens in the limit as L goes to infinity? Well, it depends upon whether or not p is bigger than 1 or less than 1. You can see that if p is 0, this is going to blow up and go to infinity. If p is 1/2, it blows up. The exponent will still be positive. But if p is 2, you get a negative exponent. So it will depend. You can see that as L goes to infinity, if P is bigger than 1, this first term goes to 0. And you end up with 1 over P minus 1. We'll distribute the negative through here and reverse the order of the subtraction. So if we get converges, if P is bigger than 1, and if P is smaller than 1, we get a positive exponent. This limit will go to infinity. And we know that even if you get equality with 1, it will still diverge. So these integrals will converge if P is big enough. If P is big enough, the function will squeeze down towards the x-axis fast enough that you trap only a finite amount of area. If P is not big enough, say we have the square root of x in the denominator, then P is 1/2, that's not big enough. It goes to 0 so slowly that you trap an infinite area. P equals 1 is the dividing line, but P equals 1 still gives you a divergent integral, the area being infinite. But anything the smallest little smidge greater than 1 for the value of P will trap only a finite area. So for example, if I'm integrating from 1 to infinity, 1 over the cube root of x, I know that this diverges to plus infinity because P is equal to 1/3, and that's less than or equal to 1. But if I'm integrating from 1 to infinity, 1 over x cubed, I know that this will be less than infinity. It will converge because P is equal to 3, and that's strictly greater than 1. You'll need to know these facts about integrals from 1 to infinity of 1 over x to the P, which converge, which diverge, later on in the course when we talk about convergence or divergence of power series. In our next example, we're going to look at what happens with exponential decay. We have a function that decays exponentially to 0. Does it trap only a finite area? You might suspect, yeah. Well, we have to back off from the problem. The problem being our upper limit of integration. And if we integrate from 0 to L, e to the minus x dx, we'll have the limit as L goes to infinity. The integral of e to the negative x is negative e to the negative x. We're evaluating from 0 to L. This gives us the limit as L goes to infinity. Plugging in L, we get negative e to the negative L minus negative e to the 0, which is 1. We get a minus minus 1. That's a positive 1. As L goes to infinity, the first term goes to 0. The area is, in fact, 1. That's from 0 to infinity under e to the negative x. In our next example, let's look at the integral from 0 to infinity of 1 over 1 plus x squared dx. You might think that when x gets big, say x is like 1,000. 1,000 squared is 1,000,000. 1,000,000 plus 1, who cares about the plus 1 at that point? The plus 1 is not going to affect convergence or divergence. This is going to look like 1 over x squared. P is equal to 2. You would suspect that this should converge. But to what? Let's find out. Let's take the limit as L goes to infinity, the integral from 0 to L, 1 over 1 plus x squared dx. Now, we need to apply the fundamental theorem of calculus. That's the limit as L goes to infinity. Do you know the antiderivative of 1 over 1 plus x squared? This is one that I asked you to remember. In fact, this is the one. We get the limit as L goes to infinity of the arctangent of L minus the arctangent of 0. Now the tangent function goes through the origin. So the tangent of 0 is 0. So the arctangent of 0 is also 0. Do you remember what the arctangent looks like? Arctangent looks like a tangent curve on the side. As L goes to infinity, this first limit goes to pi over 2. Arctangent 0 is 0. This is pi over 2. It converges. So when we integrate 1 over 1 plus x squared from 0 to infinity, the integral converges, and the area that is trapped is exactly pi over 2. If we integrate from 0 to infinity 2x over 1 plus x squared dx, what do we expect is going to happen now? As x gets big, the 1 here really won't matter. The 2 won't matter because we can move it out of the integral. X over x squared is on the order of 1 over x, and we already know that 1 over x traps an infinite area as we go out to infinity. This integral should diverge. Let's prove this. We have to back off from the problem point, take a limit as L goes to infinity. Notice that this integrand is of the form f prime over f. The antiderivative is going to be the log of the absolute value of 1 plus x squared. We get the limit as L goes to infinity. Natural log absolute value of 1 plus L squared minus natural log of 1, which is 0. As L goes to infinity, the log will blow up, and this integral diverges. It diverges to positive infinity. In my next example, I'd like to look at something called Gabriel's trumpet. Or Gabriel's horn. What we're going to do is we're going to take the curve 1 over x and revolve it about the x-axis above the interval from 1 to infinity. We will get a horn-shaped object. And here's the idea. Suppose there's a mischievous cherub who wishes to pack Gabriel's trumpet full of gold. How much volume of gold? What is the volume of gold required? In this case, we'll take little thin discs, use the method of discs to calculate the volume required to fill Gabriel's horn full of gold. Remember the formula for volumes with discs is pi integral from a to b f of x squared dx. For us, we're integrating from 1 to infinity. So in this case, we have pi, the integral from 1 to infinity. Our function is 1 over x, and we're squaring it. 1 over x squared. This will give a finite volume. A finite volume of gold is required to fill Gabriel's trumpet. Notice that Gabriel's lips must be very tiny, because this goes to 0 as you go to infinity. And Gabriel has to blow this thing from infinity. We know that this will converge. But to what? Let's calculate. It's pi times the limit as L goes to infinity. We know that you get negative 1 over x, and we're evaluating from 1 to L. It's pi times the limit as L goes to infinity. We'll have negative 1 over L minus negative 1 over 1. Of course, as L goes to infinity, the first term goes to 0. The second goes to a positive 1. So we end up with pi cubic units of gold. A finite value. This converges. So the mischievous cherub is capable of filling Gabriel's trumpet full of gold with pi cubic units of gold, a finite amount. We're not done with this example. There's more to this that might be pretty interesting, besides the fact that you get only a finite volume, despite the fact that the region goes off to infinity. It gets weirder. Yes, it is possible to fill Gabriel's horn full with paint if we wish. We could fill it with paint, pi cubic units of paint. But let's suppose that Gabriel has cleared out his horn and he wants to refinish it with gold leaf. He's going to put gold leaf all through the interior. How much gold leaf is required? In other words, what is the surface area of Gabriel's horn? Do you remember the surface area formula? The surface area was 2 pi, the integral from a to b, of f of x times the element of arc length on the side, which was the square root of 1 plus f prime of x squared dx. Let's see if we can calculate the surface area that is required in order to cover the interior of Gabriel's horn with gold leaf. So in this case, it's 2 pi, the integral from 1 to infinity, 1 over x, the square root of 1 plus, the derivative of 1 over x is negative 1 over x squared, dx. A bit problematic. This is hard to integrate. Let's simplify this. 1 plus 1 over x to the 4th. Well, what's that? I don't know. Actually, I can prove exactly what we get. We'll make a lower bound, something smaller. If I ignore some positive term in the integrand, I should get something smaller. If I just ignore 1 over x to the 4th, I'm ignoring a positive term in the integrand. I get something lower, but that lower thing, p is equal to 1. This diverges to plus infinity. Since the smaller integral diverges to plus infinity, the bigger integral must also diverge to plus infinity. So how much gold leaf does it take to cover the interior of Gabriel's horn? The answer is, it takes an infinite amount of gold leaf. The surface area is infinite. The volume is finite. Now this must be very confusing. If you want to fill Gabriel's horn full of paint, all the way up to the top like filling a glass, it takes pi cubic units. But if you try to paint the interior, the surface area that you have to cover is infinite. It's an infinite amount of paint that is necessary to paint just the surface on the inside. This is an interesting paradox, the paradox of Gabriel's horn. How can we come to grips with this absurdity? The answer can only come from the fact that our surface area formulas are idealized surface areas having zero thickness. These don't happen in reality. These are only estimations or approximations to things that might be useful. However, surface areas of zero thickness don't happen. And what is more, at some point, the amount of volume left in the tail trailing off to infinity will be smaller than the amount inside of one electron. That volume will be so tiny, you won't even be able to pack an electron into there at some point. So you won't be able to actually perform the experiment. These continuum models that we are deriving here, being extrapolated out to infinity, helps to demonstrate the absurdity of these notions in some sense. Let's look at the integral from minus 1 to 1 of 1 over x cubed dx. We have a problem at 0. we must break this into the integral from -1 to 0, 1 over x cubed dx, and the integral from 0 to 1, 1 over x cubed dx. We're only permitted to do one limit per integral. So we have to break it up in this way so that we do one limit as we go to 0 from the left on the first integral, and as we go to 0 from the right on the second integral. Keep in mind, if one of these integrals diverges, the whole thing does. Now, some of you might have been a little sly and noticed that the integrand is odd, and we are integrating from -a to a. Under normal circumstances, you could instantly declare that those integrals are 0, but you can't in this case. You just can't. The reason is, if one of these integrals diverges, the whole thing diverges, and we're just out of luck. Yes, 1 over x cubed does look kind of like this. You might think, integrating from -1 to 1, you'll have a negative area canceling a positive area, you should get 0. We're not going to permit that for improper integrals. If one of these diverges, the whole thing diverges, and we're not going to declare a value. It's not going to be plus infinity or minus infinity, it's not going to be 0. It's going to be, we declare nothing, just diverges. So we'll have to take the limit as, let's say, little l goes to 0 from the left, the integral from -1 to little l, 1 over x cubed dx, plus the limit as, let's say, big L goes to 0 from the right, the integral from L to 1, 1 over x cubed dx. We only have to evaluate one of these. If one of them goes to infinity, the whole thing is going to diverge. The other one should go to minus infinity by symmetry. Let's look at the second integral. We'll take the limit as big L goes to 0 from the right. If we're integrating x to the -3, we get x to the -2 divided by -2. And that's the limit as L goes to 0 from the right. We can write this as -1 over 2x squared evaluated from L to 1. And that's the limit as L goes to 0 from the right of -1/2 minus -1 over 2L squared. Minus is positive. L is going to 0 from the right, so the whole thing goes to plus infinity here. That means that this original integral diverges. The other integral will diverge to minus infinity. The whole thing will just be declared to diverge, and we won't specify a value. I want to look at one more class of examples. This is similar to what we did before. Before we looked at the integral from 1 to infinity, 1 over x to the p. We found that it converged if p was greater than 1 and diverged if p was less than or equal to 1. This, though, looks at what happens on the other end. 0 is the problem this time, not infinity. So we'll have to take the limit as L goes to 0 from the right, back off and then head back towards it, of the integral from L to 1. We'll write this as x to the -p and proceed like we did before. It's the limit as L goes to 0 from the right. I want you to notice the good form that I'm trying to teach you. Begin each line with an equal sign, carry the limits forward. Even though we're not actively doing anything with the limits, it's not equal if you don't write the limit. And math professors generally frown on students making false assertions. So we get x to the 1 minus p over 1 minus p, evaluated from L to 1, and that's the limit as L goes to 0 from the right, plugging in 1 over 1 minus p, minus L to the 1 minus p over 1 minus p. The 1 minus p is kind of the important point here, this power, 1 minus p. If the power is positive, then this L is going to stay up here in the numerator, and as L goes to 0, you will get convergence. So this converges to some finite value if p is less than 1. What happens if p equals 1? Well, that's not handled by this case. We'll have to do the p equals 1 case separately. If p is greater than 1, however, we get a negative. That shifts the L to the power of 1 minus p down to the denominator, and as that denominator goes to 0, the whole thing blows up to plus infinity and diverges if p is greater than 1. That leaves only one other case to check. What happens if p equals 1? As per usual, we have to back off from the problem point. The integrand has an antiderivative of log absolute value of x. The natural log of 1 is, of course, 0. Minus the natural log of L. The natural log does this. As you go to 0 from the right, the natural log goes to minus infinity. Minus infinity gives you plus infinity, and that diverges. So we get divergence to plus infinity for p-values bigger than or equal to 1. You only get convergence in this case on the interval from 0 to 1 if p is less than 1. So for example, if I'm integrating from 0 to 1, 1 over the cube root of x dx, this converges because p is 1/3, and that's strictly less than 1. So improper integrals are not integrals that say or do inappropriate things in social settings. They're integrals where the integrand is either discontinuous at some point within the interval that you are integrating on, or one of the limits of integration is infinity. In that case, you have to break the integral up into however many pieces so that you get one limit per piece. If any of those limits diverges, then the whole integral is said to diverge. And if they all converge, then the integral converges to the value of those limits.